Good evening everyone and welcome back to the second last week of problem solving session for this NPTEL course, Dynamical Systems and Control. Let's start by summarizing the contents that have been covered in the previous week. Okay, so in the last week we have gone through the optimal control design by using the Euler-Lagrange equation that is we given the cost function. We started by defining the Lagrangian and then imposing conditions of optimality, that is the Euler-Lagrange equation, in order to find the optimal control. Now in today's session we will see uh, how to modify that conditions when we have terminal cost as well. Terminal cost means if in the cost function we have some minimization with respect to the final state value as well. So suppose we have the cost function j, which is of the form s of xt, that is this terminal cost is a function of the final state or the state value at the final time t as well as the final time t, and as usual the functional, that is the function of xt, ut and t. How will the Lagrangian change if we have the terminal cost as well as the running cost? Now obviously we can have the boundary conditions. So suppose the boundary conditions are like the boundary conditions. We may be given the value at the initial time as x naught, and it may happen that our final state, that is x of t, is free and this t is also free. Okay, now if the initial state is given but the final time and final state value are free, then we will see what optimality conditions we need to satisfy in order to find out the optimal control. For such cases, when we have running cost as well as the terminal cost, we find the Lagrangian as f of x star t, like previously we have done. We have the functional f plus the partial derivative of s with respect to x, and if that's a vector then we have to take its transpose into x dot star t plus this, and then as usual the Lagrange multipliers, that is the right hand side of the function, that is f of x star, right hand side of the system, minus x dot star. Now with this Lagrangian, what are the, how will the Euler-Lagrange equation will modify? So the first condition is that it must satisfy dou L by dou x minus d by dt of dou L by dou x dot equals to 0. Okay, so that's our Euler-Lagrange equation. And since there is no u dot term, so the condition with respect to u gives us dou L by dou u equals to 0. And then for the boundary condition, we have the variation of j. If these are 0, then the variation that is left in the whole of the variation of j is L, which we have to evaluate at t into delta t plus dou L by dou x dot transpose into dou x dot, and this we also have to evaluate at t equals to 0. Now when final time is fixed, then delta t will be 0, and the only thing we need to solve is this term. This term equals to 0. Alright, or when we have final time also fixed, then x dot can also be fixed using the system equation. Then in that case, this delta x dot will also be 0. So this whole thing goes away. So the only condition we need to solve are these two equations. That depends on what boundary conditions are given to us. If both x of t and uh, t, that is the final time and final value of a state at final time, are fixed, then these two variations will also be 0, and the only equation that is left to solve is these two, and the constants can be evaluated using the boundary conditions. Now there is another approach uh, to solve this problem, whether we have a running cost or we have a terminal cost as well, is the notion of Hamiltonian. Now how to convert the Lagrangian into the Hamiltonian. So the Hamiltonian, that we generally write it as H, is nothing but the running cost or the functional plus the Lagrange multiplier into the right hand side of the system dynamics. This is how we formulate the Hamiltonian. Now if we want to write Lagrangian in terms of Hamiltonian, we can easily say that the Lagrangian is nothing but the Hamiltonian and plus the left out terms, means this term, and then this lambda x dot star term. So let's write it down. That is del s by del x del s by del t dou t, and then lambda star t into x dot star t. So that's the relation between Lagrangian and Hamiltonian. Now how those optimality conditions are translated from the picture of Lagrangian to the picture of Hamiltonian. So the optimality conditions are modified as, so the condition number 1, uh, we have to give minus lambda dot t will be equal to dou h by dou x. Okay. The second condition, uh, that is of x dot, obviously star we are talking about. This is nothing but dou h by dou lambda, that is usually with the Lagrangian. And then the third condition, that was dou L by dou u equals to 0, gets translated to dou h by dou u equals to 0. And finally the boundary conditions here gets converted to the form um, h plus dou s by dou t, that is evaluated at t into variation in final time t, plus dou s by dou x minus lambda star t evaluated at final time t dou xt. This equals to 0. Now when we have this t as fixed, so this goes to 0. When we have final state value at final time t fixed, then this also goes to 0. Otherwise, when these two uh, are free, then its coefficient must go to 0 in order to have the variation of j to be 0 at the optimal solution. Okay. Now this covers the optimal control theory for continuous time system. Now how can we extend it for discrete time system? Now let's also look how this can be extended for discrete time system. All right, now suppose that the cost function, the running cost function for a discrete time system, so optimal, this optimal control for discrete time systems. Or instead of optimal control, let's focus on optimal solutions, because control we will not derive for this course. So optimal solution for discrete time systems. Now suppose the cost function which is given to us is given as, where k0 denotes the initial time step and it varies from k0 to n minus 1, and the functional is the function of x of k plus 1, obviously, because the system dynamics is nothing but x of k plus 1 is f of xk and k. Okay. uh, Here also we need this delta j equals to 0. Now how this get translated? So for discrete time systems, the Euler-Lagrange equation is given as Euler-Lagrange equation. This is given as, so this we need to carefully carefully write. So we have to find the partial derivative of f, which is a function of xk, xk plus 1 and k with respect to x of k, and plus the partial derivative of f at the previous time step, that is x of k minus 1, x of k and k minus 1 with respect to xk, and this should go to 0. So this is our Euler-Lagrange equation for discrete time systems. Now if we have boundary condition, so that would lead us to, so this is our Euler-Lagrange, and for boundary conditions what we have, we have, again we have to evaluate f at previous time with respect to x of k, and the variation multiplied by the variation of x of k evaluated from k naught to k naught plus n, and this should be 0. Alright. Now there are two cases for it. So the case 1, for fixed end conditions, that is when both xk naught, that is initial state, and final state, that is state at xk naught plus n, are fixed. Are fixed means the variation of x at k naught and the variation of x at k naught plus n both will be 0. Okay, and when both will be 0, this term has no significance. Okay, and now in the second case, if xk naught is fixed or is given, let's write it as is given, and the final state x of k naught plus n is free, that is the case most of the time, then the variation of x at initial time must be 0. So therefore this condition will be only for k equals to x naught plus n, that is dou f star k minus 1 x star k minus 1 evaluated on x of k at k equals to k naught plus n, this should be 0. Okay, and now when we have vector, that is when xk belong to Rn, similarly when x of k plus 1 belong to Rn, then we have to evaluate f for with respect to xi's, where I is from 1 to n. So there will be n number of Euler-Lagrange equations and similarly n number of boundary conditions. So this will be replaced with xi's. All right. Now suppose that we have terminal cost as well. So we have terminal cost also present. So that will modify our cost function j as s at the terminal values, that is k naught plus n and k naught plus n, plus summation of, like previously we have done, k naught plus n minus 1 f of xk plus 1 and k. Now how will our Euler-Lagrange will modify? So Euler-Lagrange will be same as before. Means this equation will be same. Now when we have xk naught, k naught plus n, that is the final time, both are fixed, then if both are fixed, then and only the final state is free, then the boundary condition will be the same as before that we had, that is x star k minus 1 x star and k minus 1 divided by x star k and plus the terminal cost, so it is del s x star k naught plus n and k naught plus n divided by del x star of k naught plus n, and these, that is the whole of this, is evaluated at k equals to k naught plus n, because only the final state is free, everything xk naught and k naught plus n are fixed. If that is not fixed, then we have to evaluate at k naught as well. So this covers our theory for optimizing or finding out the optimal state given the cost function. Now let's try to solve few problems. So consider the system which is x dot, a scalar system, x dot equals to x plus 2u. The initial state at t equals to 0 is given to be 1. The final state value is free, so the final state is free. The cost function to minimize is this functional x square plus u square dt. The question is, find the expression, or not only the expression, I mean the solution. Find the expression of lambda with respect to time. Now let's try to solve this problem. Okay, and we will solve it you by formulating the Hamiltonian, because that is much easier instead of solving the problem by formulating in terms of Lagrangian. So the Hamiltonian is nothing but the running cost functional plus the Lagrange multiplier. Since it's a scalar case, so there will be only one Lagrange multiplier, and our system, that is x plus 2u. Okay, what are our conditions of optimality? So we know that this del h by del u should be equal to 0, and so that gives us 2u plus 2 lambda equals to 0. That means u equals to minus lambda. The second condition, that is del h by del x, it would give us 2x plus lambda, and this should be equal to minus lambda dot. So that means our lambda dot is equal to minus 2x minus lambda. And the boundary condition, that is h at t and delta t plus uh, lambda at t delta xt, this should be equal to 0. Now since this t is fixed, so this variation is 0, and this since this delta xt is uh, free, so its coefficient must go to 0, that is lambda at t, and t is 1, so lambda of 1 should be equal to 0. Now with this we have our system to solve as x dot equals to x minus 2 lambda, lambda dot equals to minus 2x minus lambda, x of 0 as 1, and lambda of 1, sorry, lambda of 1 as 0. Now with everything given, we can easily solve the expression for x and t. Now this system of equation given these terminal condition can be easily solved, as we can see that uh, from these two equations we can derive lambda dot to be equals to 5 lambda, and therefore uh, its eigenvalues will be root 5 and minus root 5. So that gives us the solution, general solution, as some constant a root 5t plus some constant b e root 5t. Now it is given that lambda of 1 equals to 0, so that would give us b equals to minus a. I'm just writing the expression, you may solve it explicitly. And then another condition, that is, since we only need to solve two constants and these can be solved using these two terminal conditions, and x of 0 is given as 1, so that would give us the expression of a. uh, because since lambda is given to us, we can solve using the expression of lambda. We can solve for x of t, So this a will come out to be minus 2 by 1 plus root 5 minus 1 minus root 5 e to the power 2 root 5. So since we have a and we have b, this lambda t, we can write it as e to the power, we can write it as um, yeah, 2 divided by 1 plus root 5 1 minus root 5 e to the power 2 root 5 into e to the power root 5, so that would be minus e to the power root 5 minus so p is 2 e to the power root 5, so e to the power root 5 e to the power root 5 into t, so it will be 1 plus t. Yes. So this will be the expression for lambda t. Okay, so the next problem is, consider this system a second order system, chain of integrator. So no, not chain of integrator, sorry. So x1 dot is u and x2 dot is given to be x1. The initial condition of x1 is 0 and the initial condition of x2 is 0, is 1. The cost function to solve is x2 square t by 2, that is the terminal cost, plus this cost u square t by 2 dt, and x of 1t and x2t are free, and we have to solve for t equals to 2. Okay, okay. Now in this question you have to find lambda 1 with respect to t, lambda 2t, x1t and x2t. So for this problem, let's first formulate our Hamiltonian. So I will write it here. So Hamiltonian, since the cost function is just u square by 2, so it is u square by 2, and since it's a second order system, so we will have two Lagrange multipliers, so lambda 1 u plus lambda 2 of x1, so lambda 1 u plus lambda 2 x1, and the terminal cost that is given to us is x2 square t by 2, so it is x2 square t and divided by 2. Okay, now let's impose the conditions of optimality. So the del h by del u should be 0, so that would give us the expression u equals to minus lambda 1. Okay, and the second, for lambda dot equals to minus del h by del x, this would give us first with respect to x1, so this would give us lambda 1 dot equals to lambda 2, and with respect to x2 for lambda 2 dot, this would give us 0. Okay, now we have everything. So from here, since lambda 2 dot is 0, means lambda 2 must be, lambda 2t must be a constant. Let's call that constant c1. And now since lambda 2 is a constant, which is c1, so that means lambda 1t would be nothing but so this is minus, so that means lambda 1t is nothing but the integration of this constant, that is minus c1t plus the constant of integration, that is c2. Now we have the expression of c1 and we have the expression of c2 with us. Okay, let's see what we can do for x1 and x2. Now x1 dot was given us to be u, and u we know is minus lambda, and lambda 1 is, we know, is a constant. Sorry, lambda 1 is, so it is c1t minus c2. So that means from here we can integrate this term to get x1. So x1t will be c1t square by 2 plus, sorry, minus c2t and plus c3. So this is the expression for x1. And similarly we can see that this x2 dot t, x2 dot is nothing but x1. So x1 if we integrate will give us x2. So x2t is the integration of x1. So it is c1t cube by 6 minus c2t square by 2 plus c3t and plus c4 the constant. This is the expression for this. Okay, but how can we solve these four constants? For that we need to analyze the boundary conditions. So two boundary condition we have that would allow us to solve for two constants, but we need extra two conditions in order to solve two another constants. So first condition is given to us, x1 at 0 is 0 and x2 at 0 is 1. Now let's now since it is given that the final t is free, now if final x of t is free, so when x of t is free, that means that when this is, so this is fixed, so this is 0. Now when this is free, we have this coefficient should be 0 in order to have delta j to be 0. So for this coefficient to be 0, we have to derive del s by del x minus lambda to be 0. So let's do this. So that is del s by del x minus lambda should be 0. Now what is del s? So s is just x2 square by 2. So its derivative with respect to x1 is 0 and lambda 1 will be 0. So at t. So lambda 1 at 1 is 0. Alright. And its derivative, so this is for x1, and with respect to x2, it will give us x2 only. So x2 at t minus lambda 2t equal to 0. That means lambda 2t equals to x2 t. That means so the time we are considering is 2. Yes. Okay. So this t is 2. So this will be 2. Okay. That means lambda 2 equals to x2 of 2. Okay. So we have one condition, we have second condition, we have third condition, and we have fourth condition. So now using these four conditions we can find these four constants C1, C2, C3 and C4. So let's see. Okay. Um, let's go with lambda 1. Now since we know lambda 2 is C1, so lambda 2 is C1 means it will be constant for all time, so this is also equal to C1. So x2 at 2 is C1, so x2 at 2 we can solve. So let's write x2 at 2, this is equal to C1, and the expression we can put t equals to 2 here. That would give us C1 8 by 6. Okay, and then we can put t equals to 0 here for x1 0, and x1 0 is given as 0, so c3 comes out to be 0, so c3 equals to 0. And here also at t equals to 0 we know x2 is 1, so this 1 equals to 0 0 0, so c4 will come out to be 1, so c4 is 1. And the last condition we have lambda 1 2 equals to 0, so lambda 1 at 2 equals to 0 minus 2 c1 plus c2, so c2 equals to 2 c1. We can put all these three over here, so that would give us c1 to be 3 by 11, c2 to be 6 by 11. Okay, and c3 is 0, c4 is 1. So this would give us the solution for this lambda 1, lambda 2, x1 and x2. Okay, let's solve another problem. Just give me a minute. Let's take another problem. We have x dot. Consider the system 3x plus 2u with the cost function to minimize is the terminal cost 5x square t plus the running cost 5x square t plus 4u square t dt. It is given that t and x of t are free. For this problem, you have to find the terminal relation between x and lambda. That means you have to find the relationship between x of t and lambda of t as some function. Now since t and xt both are free, their coefficients must also go to 0. So the coefficient for delta t is h plus del s by del t at t. This should be 0 because that is the coefficient of delta t, and at the same time del s by del x minus lambda at t, this should also be 0. Now when we do evaluate this, it will give us del s by del x is 10x, so it is 10x of t just a minute, I think. Okay, let's solve and then we will see. So that this gives us 10 of xt equals to lambda t, and when we solve this one, so this is equal to h. So the Hamiltonian is this expression. It is equal to, so h plus del s by del t at t this equals to 5x square t, 4u square t, lambda t, 3xt, 2ut, and plus 10x t. No, there is no del s by del t term, so this term will not come, so this will be 0. Now when we solve del h by del u equals to 0, we will get 8u plus 2 lambda equals to 0, or we will get lambda equals to minus 4u, or u equals to minus 1 by 4 lambda. If we replace that over here, that would be, so u square is lambda square by 16, that is lambda square by 4, 3xt, and this is 2ut, so 2ut means minus lambda t by 2 is equals to 0. So that's the expression of at the final time t. All right. So in the next problem, consider system x plus 3u x0 as 1. Cost function is x square t, 0 to t x square t, 3u square t dt. It is given that the final time is free, but the expression for final state is related to t square, that is it is equal to t square. Then how we can solve? Now since x of t equals to t square, so that means uh, the derivative of xt with respect to xt will be 1, and then the variation of x of t, then partial derivative of this will be 2t and delta t. So that means that the variation of x of t is related to the variation of t by the factor 2t. Now this will be helpful in solving our boundary condition variation condition of J. So we know that at optimal solution, the boundary condition give us this condition, obviously at t delta t. plus lambda delta xt. This should be 0. And this expression can be replaced with this expression. So when we do that, so now since we have delta t in both sides, we can write h plus delta s by delta t plus 2t into del s by del x minus lambda delta t equals to 0. Now since t is free, this delta t is not equal to 0, so its variation its coefficient should be equal to 0. So this whole expression should be equal to 0. Now if this whole expression is 0, we can evaluate it. So h for our case is x square t plus 3u square t plus lambda t x of t u of t. So this is h. Now del s by del t is 0, and then we have 2t. Del s by del x is 2xt, so it is 2xt, and then minus lambda t. This is our terminal condition. Okay, let's do one problem on discrete time systems. Then we will stop. Consider the cost function j it is given as summation k varying from k naught to k naught plus 2 to x of k plus 1 x square of k plus 1. So this is our cost function, and the initial state value is given to be 2. The final state value, that is k naught plus 3, it is free. Okay, now if that is the case, we first have to solve our Euler-Lagrange. Now what is Euler-Lagrange for discrete time system? We have to first write f of k, or yeah, so what is f of k? Basically f of xk is k plus 1 and k, so it is this right hand side, so it is 2x of k, x of k plus 1 and x square k plus 1. Okay, now we have for Euler-Lagrange we have to solve del f at k, that is xk, k plus 1 and k with respect to del x of k plus del of xk at minus 1. So xk will be xk minus 1, xk plus 1 will be xk, and k will be k minus 1 with respect to x of k. This should be 0. Now when we do for this system, so this expression is nothing but its derivative with respect to xk, so it is 2 of xk plus 1. Now when we do this at k minus 1, so this will be x of k minus 1, this will be xk, and this will be x square k. So the partial derivative with respect to xk will be 2 times of xk minus 1 and 2 times of x of k. This should be 0 for k naught, for k equals to k naught plus 1 and k naught plus 2, because this is where the cost function is defined. Now these two will cancel out, so the expression that we will have is x of k minus 1 plus x of k plus x of k plus 1, this equals to 0. Now we can iterate this for k equals to k naught plus 1 and k naught plus 2. So let's evaluate it at k equals to k naught plus 1. So that means it will give us x of k naught, x of k naught plus 1, x of k naught plus 2 equals to 0. And it is given to us that x of k naught equals to 2. So this term is 2, that means x of k naught plus 1, x of k naught plus 2, this equals to minus 2. Alright. Now let's again solve it at k equals to k naught plus 2. So that would give us k naught plus 1, k naught plus 2, k naught plus 3. This should be 0. And from here this term is minus 2. So this term will be minus 2. That means our x of k naught plus 3 is equal to minus 2. Or sorry, plus 2, because minus minus will be. So it is. Now it is given to us that our final state is free. Now since final state is free, that means uh, we have to use the terminal condition for final time only. So del of f at xk minus 1, xk and k minus 1 at x of k evaluated at final time, that is k naught plus 3. This should be 0. Okay, from the conditions that we have written over here, because this xk naught is free, so therefore only this coefficient will be 0. Okay, now this is nothing but this expression only at k naught plus 3. So let's write it. So this will give us 2, what is it, 2 xk minus 1 plus 2 xk at k equals to k naught plus 3 equals to 0. That means x of k naught plus 2 plus x of k naught plus 3, this is 0. Now since x of k naught plus 3 is 2, that means x of k naught plus 2 is equal to minus 2. Now since we have calculated x of k naught plus 2, we can solve x of k naught plus 1 from here. So our x of k naught plus 1 will be minus 2 and plus 2, so that will be 0. Okay, so we have calculated all the expressions. So x of k naught was given as 2. Let's write it neatly. So x of k naught was given to us as 2. X of k naught we calculated, k naught plus 1 we calculated as 0. X of k naught plus 2 we calculated as minus 2. And x of k naught plus 3 we calculated as plus 2. So the sequence of x is 2, 0, minus 2 and 2. So this is our optimal solution. Now in a similar way other problems can be solved. If terminal cost is also given to j, then we can solve the Euler-Lagrange, and then we need to also solve the boundary condition, that is and that depends on what uh, what is given as free and what is given as fixed. Then in that way the boundary condition will modify, and if we have a terminal condition as well, so that also adds on the boundary condition to have the whole of the variation to be 0, and in that way the sequence of the optimal solution for a discrete time system can easily be calculated. Okay. Now in the next session, that will be the final session for this course, we will discuss various notions about discrete time systems. Here we have seen how we can calculate the optimal solutions for discrete time system. Now we will see how different notions like controllability, observability and all those things, uh, how they are defined for discrete time systems, as we have already covered these notions for continuous time systems. So that's all for today. Thank you for joining today's session.